Hello friends, welcome back to my channel Chemistry with DB. So this is the second part of this video on electrophilic addition reactions. I'm going to explain how these electrophilic addition reactions take place in case of asymmetric alkenes. So first of all, let's see what is a symmetric alkene. A symmetric alkene is one in which the double bond is symmetric or it's balanced in between. That means there is a symmetry we can see about the double bond. Same we can see in case of but2ene. Here also I can see a symmetry because the two sides are mirror images of each other. And when these react with HCl, then in that case HCl or HBr, then in that case any electrophilic addition reaction will give you only one isomeric product. Because it doesn't matter whether this particular hydrogen goes with this carbon or this carbon. However, in case of asymmetric alkenes, it makes a difference whether this hydrogen is going with this carbon or with this carbon. If, let's say, I name these as this one is number 1 and this one is number 2. So, if the hydrogen goes with the number 1, then in that case, the product is going to be and you would get a Cl over here. Right, and in case this hydrogen had gone with the number 2 carbon, then in that case the product would have been 1 chloropropane, and here it was, this is 1 chloropropane and this is 2 chloropropane. Now which one is going to be more or major product, that is going to be decided by the Markownikoff's rule. Now Markownikoff's rule says that the delta positive hydrogen electrophile that's going to join the carbon atom in the C double bond C, which already has more hydrogen atoms attached to it. So now let's see it in context with the propene that we just saw. So when we have propene, so the number 1 carbon has got 2 hydrogens attached to it, and this one has only 1 hydrogen attached to it. So therefore, as per the Markownikoff's rule, the hydrogen in the HCl, which is the delta positive electrophile, and chlorine was delta negative. So this delta positive hydrogen will join this carbon and number 1 carbon, and the product that it will give you would be 2 chloropropane. This would be the major product, and the minor product will be 1 chloropropane, as we have just seen, because in this case hydrogen is less likely to join the number 2 carbon, and therefore because of the Markownikoff's rule. So this is going to be the minor product. Now what exactly decides about this Markownikoff's rule is the types of different carbocations. We have primary, secondary and tertiary. Primary carbocation is one which is bonded to only one alkyl group. So you can see that this is the one alkyl group that this carbocation is bonded to. In the secondary carbocation, the carbon is bonded to 2 alkyl groups, and in case of tertiary, the carbocation here is bonded to 3 alkyl groups here. Now the alkyl groups have a tendency to push electrons towards the carbocation that they are bonded to, and as a result the positive nature of the carbocation becomes a little bit less positive because of the electron pushing happening, and that stabilizes the carbocation. Stabilizing of the carbocation means that the it's more likely to form, and the more alkyl groups attached to the carbocation means more inductive effect, and therefore it is likely to be more stable. As a result of this, we can see that to explain it further, we can see that in case of a primary carbocation, the electron pushing will be happening from this one alkyl group, whereas in case of a secondary carbocation, because it's bonded to 2 alkyl groups, the electron pushing will be happening from two ends, both the alkyl groups. And in case of tertiary, the electron pushing is happening from three ends, and this is why most inductive effect will be felt in case of a tertiary carbocation from the three alkyl groups. Now that decides the stability of the carbocation, as I've just told you. As a result of this, the tertiary carbocation is the most stable and more likely to form as compared to secondary carbocation, and secondary carbocation is going to be more stable than the primary carbocation. Primary carbocations are going to be least stable. Now let's see this in just looking at an example of this electrophilic addition reaction of 2-methylbutadiene with HBr. So we can see that as per the Markownikoff's rule, I can see that this carbon doesn't have any hydrogens attached to it, whereas this carbon has got one hydrogen attached to it. So therefore, as per the Markownikoff's rule, this delta positive hydrogen in the electrophile, this is going to join the carbon with more hydrogens attached to it. So therefore, it's likely to go here in this place, and the carbocation that is going to be formed will be a tertiary. Tertiary carbocation is likely to form because that is more stable than the in the other case. If the hydrogen had gone to this carbon, then in that case the product would have been the carbocation that would have formed as an intermediate would have been a secondary carbocation. And you know that the tertiary carbocations are more stable than the secondary. So therefore, when the bromide ion forms, that bromide ion is more likely to join this carbocation, and as a result, what you would be seeing is you would see this as the major product in this reaction. So, and how would we name this? This would be 2-bromo 2-methyl-butane, and the minor product is going to be two bromo 3-methyl-butane. So this is going to be the minor product. I hope you were able to understand through my explanation how does the electrophilic addition reaction for asymmetric alkene works. If you like this video, then please like, share and subscribe, and I look forward to see you on my next video. Thanks for watching. Bye. Take care.